in this lecture we are going to talk about constant on off time mixed signal current mode control architectures. So, first we will talk about the steady state operation under mixed signal constant off time current mode control. Then what is the complete architecture of mixed signal constant off time peak current mode control. Then constant on time valley current mode control, a mixed signal architecture, and what are the applications as well as what is the difference and similarity, what are the benefits and shortcoming in constant on off time mixed signal architecture, that will also discuss. So, in this lecture first we will talk about mixed signal peak current mode control architecture. If we talk about, if you recall the fixed frequency control, then here only the difference will be the modulator. So, this modulator will be different, otherwise you have a analog comparator, then you have a A to D converter, D to A converter. So, this thing we have discussed in the in this week, particularly subsequent lecture, previous lecture we have already discussed in detail. And in this paper it has been reported that if we use a mixed signal like a fixed frequency peak current mode control, then if we try to increase the gain of the controller, that means if we want to increase the, let us say, if you want to speed up the response by increasing the controller gain, then it will lead to structurally unstable behavior. That means it will lead to duty ratio saturation problem, and that means there will be subharmonic instability, but it will also lose the structural stability. But in this paper it is also discussed such structural stability will not be lost in variable frequency control. And we have discussed in the previous lecture what is the mixed signal constant off time current mode control, and we have discussed that if we trigger, that means if we link the sampling with the monoshot timer event, that means here as if we are sending the sampling command before the monoshot timer finishes is counting, then we can provide some delay for conversion and computation time, and the current difference will be updated accordingly. Now, in this timer there is a monoshot timer, and this monoshot timer will be loaded with a constant off time, that is the timer, and there will be a minimum on time, and this logic we have discussed in detail in our NPTEL lecture in the previous lecture, because if we want to avoid a potential collapse, then most of the commercial product use a minimum on time, and that we know. And in case of constant on time control, there is a minimum off time. So, these two parameters are there which will avoid that such modulation may not lead to a complete collapse of the system. Then if we take the full structure of the constant off time control, then we need to actually compute this A to D converter. That means we need to sample the voltage of like A to D converter using the A to D converter. That sampling should be with respect to the event. So, when you say the event, this is a clock which will generate the event, and that will sample the A to D converter. The same clock should be used to sync with the controller computation. Okay, that means, but there can be a time shift because the computation may happen after some time. That means it may not be exactly at the same time of the sampling. Whenever you send the sampling command, the computation should happen a little later, because that will accommodate the conversion time of the A to D converter. And then the event can be detected from the comparator output. So, whenever this comparator goes high, then we will detect the event, because suppose if you are talking about a constant off time, that means this is a peak current difference, and we are talking about the inductor current. That means whenever inductor current. So, whenever the inductor current hit this peak current, so this is the limit, whenever it hit we take the sample, but practically we cannot turn off immediately because there will be a driver delay and all. So, the current will potentially go a little bit later. That means this will be a delay, this delay tau d due to the driver delay, maybe dead time delay. So, you cannot turn off. So, that means whenever you see the comparator hitting, the current is actually hitting the reference current, then you send the sampling command and that can be generated. So, that means we can get the clean sample, but this should be delayed, phase shifted, because the computation cannot happen immediately, because only the data should be available. So, this is a full architecture, and the monoshot timer, the detailed description, that means if you go inside the monoshot timer, there will be a time delay, and this is the delay is the minimum on time. So, this is our minimum on time if we want to avoid a complete collapse of the system, minimum on time, and this is there in all commercial product. And if you talk about constant on time, there will be a minimum off time. So, this is the typical implementation. In fact, this implementation aspect other than this sampling clock we have discussed in our NPTEL previous lecture. The only thing in digital we need this clock edge to, this is the event with respect to this event we are going to synchronize the sampling and the computational process. So, in constant on time, off time, this is with one cycle delay, that means you can provide sufficient delay for the conversion and computation, okay, and this will also have potential problem in terms of stability and performance. If you go to constant on time, so this architecture also we have discussed. Here it is like a valley current mode control, that means when the inductor actually hit the lower limit current, that means whenever the inductor hit the lower limit, then you actually turn off the, that means you should send the sampling command, but since there is a delay, so essentially the current will go a little further down. So, this delay, that delay is due to driver and the the delay due to the driver as well as the delay of the dead time, and you can take the sample here, and then the output voltage will have a clean sample because there is no switching event at that time. I am talking about this particular time. So, this is a minimum off time you have to provide for constant on time control, and the on time is loaded in the monoshot timer. So, everything else structurally almost remains same, only some logical blocks will be different under this, and either you can change the terminal of this inductor current, the reference current, or you keep it same and you can take care in the internal logic here. So, this is the constant on time current waveform. Here you can see, if we take the, it is one cycle delay, that means if you take the sample whenever the monoshot timer is about to turn on, that means this again it will be delayed, that means whenever the monoshot timer actually the current hit the reference current limit, then actually you send the, because it is one cycle delay. So, whenever it hit the current limit, then you send the sampling command, but there will be a small delay, actually the current should little bit go down in this case, and then it will go up. Okay. So, if we take the here, so it should be, the current should actually go, current should go a little bit this side and then it will up, because this is the time, the dead time, delay due to the driver as well as the dead time. So, that time you can take the sample and you can use in the next cycle. So, it is a one cycle delay. So, otherwise it is same, only fundamentally the how this modulation and the timings parameters are generated, that is the difference. Now, we want to compare, and it is reported in this paper that in fact it is well known, the constant of time. So, this is our constant of time current mode control, and this is constant on time current mode control. So, we want to see what are the applications, right. First of all, both of them can be used for wide duty operation, because we have not discussed with, about the inner loop stability. If we discuss the inner loop stability, then both of them offer inherent current loop stability, inherent current loop stability. That means the current loop is stable for both the cases. So, inherent current loop stability, it is applicable. So, that means you can use for wide duty operation any of this technique. But if you take a buck converter for constant off time control, we are essentially controlling the peak current. That means what you need to sense? You need to sense high side current, sense high side. If you sense the full current, then you can implement any of this control logic. But if you want to specifically only want to implement constant off time, you need to sense the high side current. Here you need to sense the low side current. this is for a buck converter. It will be the opposite for a boost converter. So, it is easy to sense low side current for a buck converter because the low side switch is a ground refer. So, you can simply put a resistance or you can take the advantage of RDS on. So, it is reasonably easy, and that is why if you go to the commercial multi-phase product, in fact the majority of this product they use a constant on time control because they can sense the low side current. Similarly, if you are talking about a low smaller on time or longer off time, then you will get longer duration to sense the current. That means it is a valley architecture. So, you will get sufficient time for sensing and computation. Similarly, if you are talking about a longer on time, then this technique may be useful because if the duration is very short, then sensing, because this always the current sensor will have some spike here, high frequency current sensor. So, some portion of this current has to be blank, that means you cannot compare, otherwise you will false trigger. So, you will have a limit on the duration which you can get the clean current signal, and you have to compare with the other analog current reference. So, that means if you get a longer duration, then you can actually wait so that the transient part is removed and you can compare. So, you do not need a very high speed comparator, but if the duration is very small, then it will pose a constraint and it may not be able to implement the mixed signal architecture because of the sensing noise in the analog current. So, that is why even though both can be used for wide duty ratio operation, but the duration of the time for this, the critical duration is that your on time duration has to be longer, on time critical, because if the on time is not sufficiently large, then you cannot do any comparator action, but you can make a very small off time because it is a constant off time, there is a timer circuit. Similarly, the off time current off time is critical here because you need to take the action during the off time. So, based on that, if you are going for low duty ratio buck converter or high step down buck converter, then this will be more suitable constant on time than constant off time, and that is why the major of the commercial products are coming. And if you go to the multi-phase product, low voltage high current application, most of these people go for constant on time control, and it is a very well known control technique. So, that means depending upon the duty ratio you have to select. The another aspect, that means the first point is that your duty ratio, or I will say not duty ratio because it is a variable frequency modulation, I will say the conversion ratio. That means the voltage conversion ratio. So, low conversion ratio constant on time is preferable for buck, it is the opposite for boost, and high conversion ratio constant off time may be preferable. Number 2 is that, what is that? The conversion ratio is 1 is the light load efficiency. So, light load efficiency, so it is well known, in fact we have discussed in our earlier NPTEL lecture that constant on time control, if you operate in discontinuous conduction mode under light load, it offers the switching frequency linearly varies with the load current, that is the property it holds. That means, if you apply constant on time with under discontinuous conduction mode in light load, and if the load current decreases, then switching frequency will linearly decrease. As a result, it will save the switching loss and it can improve the efficiency, and that is why most of the PFM technique, if you go for PFM pulse frequency modulation, they by default use this constant on time modulation or its derived version, either direct constant on time or it can be peak current difference based constant on time equivalent to this, or it can be adaptive on time. So, either constant on time or something called adaptive on time control. So, in this paper we have also discussed, these are all well known. The third one is the transient response. So, suppose I am just considering a inductor current reference like this, and there is a load transient. Okay. Now, when there is a load change, that means this was my initial load current. So, this was my initial load current. Now, here the load current got changed. Let us say it goes here. Now, the inductor current has to change its value. So, if you go for constant on time control, so if the on time is constant, then after the constant on time, it will undergo a minimum of time. So, it will go like this. Okay. So, that is the problem under constant on time because of minimum of time, because if you want to speed up the response, you want to slew up this current. That means you want to as fast as possible increase the current, and but constant on time, because of the minimum of time, it will slow down. But if you take the constant off time control, the same waveform, only let us say we are talking about constant off time. So, it will simply slew up and it will hit the peak current reference and then it will come back. So, it will go like this. So, that means in terms of transient response point of view, so this is like a constant off time, that means this is coming from here, and this logic is related to constant on time because of minimum of time. So, that means for step up transient, constant off time by default is better than constant on time. So, that is why many commercial products, they want to adjust or they may disable this minimum of time during the slew up process in order to speed up. That is one possibility. But if you do not alter such constant minimum of time duration under constant on time modulation, then you will end up with this, you will suffer from slower step up transient. But if you take the step down transient, it will be just the opposite. In step down transient, the constant off time has a minimum on time. As a result, it cannot slew down. That means if you take the other transient effect, so suppose in a constant of time, it will go, it will go like this. So, this is under constant of time. So, it will penalize the step down transient. But if we talk about minimum constant on time, if we talk about the constant on time control, it will simply go on. So, this is under this technique and this green one is using this technique. That means this green one is using this technique. So, that means the transient response point of view, constant off time is good for step up transient, constant on time is good for step down transient, and in this paper we have shown that if you hybridize this constant on off time with some minimum changes in the architecture, you can retain the fast transient response for the either configuration. Okay, and then you can further optimize the performance by tuning the controller. So, in summary, we have discussed steady state operation under mixed signal current mode control in using both constant off time as well as constant on time architecture. So, constant off time is the peak version of the current mode control, constant on time is the valley version of this, and we have discussed some aspect of application of mixed signal constant on off time current mode control architecture. And we saw that for wide duty ratio operation, which is useful in terms of sensing current, in terms of duration of on and off for taking the comparator action, in terms of transient performance, and also in terms of light load efficiency. And we want to see some of this aspect when you go to actual hardware implementation or maybe the MATLAB simulation, some case study we can show, and we will show that why these techniques are gaining popularity, the variable frequency control, and that also we want to see at some hardware case study. So, with this I want to finish it here. Thank you very much.